Hello my precious friends, welcome to our today's class. It's our 7th lesson on the first topic of Form 3 work, which is called linear motion. As usual, let me comment by giving you the quote of the day, which states that the greatest wisdom is to get to know oneself. This quote was first discovered by an Italian physicist, mathematician, and philosopher by the name Galileo Galilei, who made greater contributions to the discovery and also the construction of the first symbol pendulum. So we shall discuss his contributions towards the discovery of the first pendulum at the end of our lesson today. So a pendulum is a body suspended from a fixed point so as to swing freely to and fro by the alternate action of gravity and momentum. So when we talk of a pendulum, we usually take a bulb or just any somehow some heavy body, but a smaller one, then we suspend it in free air. Then of course we displace it through a very small angle. So it is usually a small angle so that to reduce the air resistance acting on it. That means that if you you release a bulb or a pendulum from a certain height, then you allow it to swing freely in a vacuum, then we expect such a bulb or a pendulum to swing henceforthly. That is, it won't stop swinging in a vacuum because there is no air resistance to stop it. Otherwise, if you displace it in a region where there is free air, it means air resistance will always be acting on it. Then after some time, we expect it to stop oscillating. So we talk of one complete oscillation if our bulb moves from point A to point C and back to point A. So when the bulb swings from point A to point C and back to point A, that is when we count a complete oscillation, because from point A to point C, that is half an oscillation. From point C back to point A, that is another half an oscillation. So half an oscillation plus half an oscillation, you get one complete oscillation. Then in such experiments, you are usually given the length of the string that is used to tie your bulb or that is making the pendulum. We usually vary the length, then we record the amount of time taken for a given number of oscillations. For example, in this experiment, when the length of the string is this particular length here, when it is 20 centimeters, it is observed that the bulb swings from point A back to point C, back to point A for 20 oscillations. So for 20 oscillations, the time recorded is 8 seconds. Then when the experiment is repeated again for 20 oscillations, the time recorded is around 12 centimeters, so to 12 seconds. So to find the average time taken, we shall simply take 8 seconds plus 12 seconds, then the answer, that will be 22. Then we divide by 2 to get our average time taken, which gives us 20. That is 8 plus 12, we get 20. 20 divided by 2, we get 10 seconds. Then of course, to find the period is the time taken for each oscillation. And if we are talking of 20 oscillations are taking a time of 10 seconds, then each oscillation will take, that is, we shall take the time taken for each oscillation, we shall take 10 divided by 20 oscillations, which gives us 0.5 seconds as our period. Then the square of the period, we shall simply take 0.5 squared, which gives us 0.25 seconds squared. Of course, you repeat the same for other values, that is for when the length is 30, when the length is 40, and also when the length is 50. Now, it's important also to remember that whenever we are talking of practicals involving the pendulum, usually the graphs are usually straight line graphs. Sometimes it can be straight line graph from the origin, that is from point 0,0. In other cases, it can be a straight line graph starting from somewhere within the t squared axis or within the time axis. But for all questions involving the pendulum, this is usually the equation that governs such a swing or such a motion, which states that the period of the motion of a pendulum is equals to 2 times pi times the square root of the length of that particular rope or maybe string that is tying our bulb, then divided by g. Of course, g is the acceleration due to gravity. So this is usually the equation that governs all motions under a symbol pendulum. So that means, and we have also said that all graphs for simple pendulum, that is most graphs for simple pendulum, are usually straight line graphs. So that means we shall be comparing this particular equation with the equation of a straight line graph. Then usually you are asked to plot some graphs. So these are the possible graphs. So the first graph is a graph of t squared, that is period squared, against length, that is this particular length of our bulb here. And such a graph is usually a straight line graph. And if your graph is starting from the origin, it means this was the equation will be of this particular format here. Remember, all the equations are usually obtained from the equation of the period, which is period is equals to 2 pi root L over G. So the first task is to make our equation here to rhyme with the quantities on our graph. Remember, on our graph, the vertical axis is having t squared, then the horizontal axis is having length L in meters. Usually, if it is a practical, you can be given another column for converting the length into meters, whereby you will just be dividing by 100. For example, 20 divided by 100, you'll obtain something close to 0.2 meters, because we know the SI unit for distance or length is usually the meters. So to make our graph rhyme with to make our equation rhyme with the graph, we shall just ensure that we have t squared on the y-axis or on the vertical axis. So the easier way of obtaining that is by, first of all, squaring both sides of our equation here. So if I square both sides, I'll have t squared being equal to, if I square this side, I'll have 2 pi squared, then also root L over G, I also square it. Remember, I'm squaring so that I can obtain my t squared being on the vertical axis and my L being on the horizontal axis. So t squared, I'll simply obtain t squared. Then 2 pi squared, 2 squared, I'll get 4. Pi squared, I'll get pi squared. Then, of course, the root of LG squared, the square and the square root will cancel out, so that we just remain with L over G. Then remember that these graphs are usually straight line graphs, so we can compare with the equation of a straight line graph, which is usually y is equals to mx plus c, where y is the y-axis, of course m is the gradient of the graph, and x is the horizontal axis, and of course c is usually the y-intercept. But what is on our y-axis in this particular case is the t squared. That's why I'm rearranging it such that y is in the position of t squared. Then, of course, what is on my x-axis is L. So L rhymes with my value of x. Then, of course, my graph is starting from 0.00, meaning that my t squared axis or my y-axis is 0. Therefore, I'm adding my 0 here. Therefore, the value of c is 0. So whenever the value of c is 0, that means your graph will always start from the 0.00 or the origin. Then clearly m will represent the gradient of that particular graph. So that means that our gradient m will be given by 4 pi squared over g. So you can see that 4 pi squared over g is rhyming with my m, and usually from mathematics m usually represents the gradient of the graph. So m is equals to gradient, which is equals to 4 pi squared over g. In case you are asked to find the value of g, which is usually the gravity, you simply multiply both sides by the LCM, so that you have g times gradient being equal to 4 pi squared times g. Remember, g and g will cancel out, so that we remain with 4 pi squared. Then, of course, if I want g, I'll divide both sides by gradient, so that g will be equal to 4 pi squared divided by the gradient of such a graph. Another possible graph from the equations of pendulum is usually the graph of t against the root of L. Remember, this particular graph here, graphs for pendulum, usually most of them are usually straight line graphs, and we have said that the equation governing motion of a pendulum is usually the equation of period, which is period t is equals to 2 pi root L over G. Of course, from this, we just try to play around with this particular equation, so that we have t on our y-axis or on the vertical axis and root L on the horizontal axis. And of course, the easier way of obtaining that is, first of all, squaring both sides of this particular equation, so that we have t squared being equal to 2 pi squared root L over G squared. Then, of course, after that, I'll have t squared being equal to 2 squared, I'll get 4, pi squared, I'll get pi squared, Then of course the square and the square root will cancel out, so that I remain with L over G. So I have L over G. Then of course, if I want T alone, I'll now take square roots on both sides again, so that I remain with T. So the square root of T squared, I'll just take square roots on each and every side of this particular equation here. Square root of T squared, I'll get T. Square root of 4 pi squared, I'll get 2 pi. I'll have 2 pi. Square root of L, I'll just have root L. Square root of G, I'll just have root G. So of course, I've converted this equation in such a way that my y-axis from this particular, my y-axis is having T. So you can also see that I have T here. My x-axis is having root L. You can also see that I have my root L here. So because again, we've said that all those particular graphs will be straight line graphs, we compare with the equation of a straight line graph, which is usually y is equals to mx plus c. So of course, y is rhyming with the values on my y-axis or the vertical axis. My x is also rhyming with the values on my x-axis, which is the root of L. Of course, after arranging that, the m, what will be in the position of m, is usually the gradient, even from mathematics. Therefore, m will be equal to the gradient, which is equals to, m is equals to gradient, which is equals to, my gradient here is 2 pi over the root of g, 2 pi over the root of g. Of course, if I want to find g, I'll multiply g, root g on both sides, so that I have root g times gradient being equal to 2 pi times the root of g. Of course, root g and root g will cancel out, so that you just remain with 2 pi. Then if I divide both sides by the gradient, I'll now have root g being equal to 2 pi divided by the gradient. If I square both sides so that I remain with g alone here, remember the square of root g will remain to be g. Therefore, g will be equal to, if I square again this side, 2 squared, I'll get 4. Pi squared, I'll get pi squared. Then, of course, divided by my gradient, divided by the square of my gradient. Therefore, g will be given by 4 pi squared divided by gradient squared, divided by the square of my gradient. So that will be the value of the gravity. Then of course, for this other case, we can also have a graph of T squared against L, just the same as this particular graph here, only that the difference is that for this graph, it was starting from the point 0, 0, but this other graph is cutting the y-axis at a point, say, at point 2. So, of course, the equation governing this particular motion here is just the equation of the period, which is t is equals to 2 pi root L over g, which also will just disintegrate into the equation of what? T squared is equals to 4 pi squared L over g. But if your graph is cutting through at a certain point on the y-axis, of course, at a point which is not 0, 0, for example, at a point 2, then it means in that particular case, your value of c will have something, that is c will not be 0. For example, here, if you are given the equation t squared is equals 4 pi squared L over g plus pi over k, where pi over k will always be the value on the t squared intercept or the y intercept. So, like for this particular graph here, as you can see, it is starting from 0, 0. That is why my value of c is also 0. But if your graph is cutting the t squared axis or the y-axis at some certain point other than 0, 0, for example, at a point 2, then we expect your equation to be t squared is equals 4 pi squared over g, 4 pi squared L over g plus a given constant. For example, in this particular case, the constant is pi over k, pi over k. Remember also, you cannot have an equation that is a graph of t squared against L, whereby your line is cutting the negative of t squared axis. Because remember, period being a scalar quantity, it can never be negative, because we know that you cannot have a negative time. And remember, period is just coming from time, whereby period is the time taken for one complete oscillation. So because time is a scalar quantity, it means that it can never be negative, and therefore it is not possible to have your graph cutting towards the negative side of your t squared axis. Therefore, all graphs will either cut on the positive side of your t-axis, or they will be starting from your point 0, 0. That is whenever you are dealing with a pendulum. Therefore, if maybe you are given a certain value of you are given such a graph, then you are asked to find the value of the maybe a given constant. For example, in this particular case k, you just equate your value of c with the value of the constant from your graph. So because c is equals to pi over k, we shall say that c is equals to pi over k, which is equals to, from the graph, our value of c is 2. So you equate pi over k to 2. Therefore, if you want to find the value of k, you simply multiply both sides by k. So I can extract this one so that I have pi over k being equal to 2. Pi over k is equals to 2. If I multiply both sides by k, I'll have 2k is equals to pi. 2k, pi being equal to 2k. Then I divide both sides by 2 so that I have 2 over 2, which cancels out. Then I remain with pi over 2. Therefore, k will be equal to pi over 2. If you are given the value of pi, of course, you substitute the value of pi. Let's look at sample, that is examples of such questions. So you are given that the table below shows values obtained from a pendulum experiment. You are required to use it to answer the questions that follow. So usually in the questions, that is in the practical questions, you are usually given the values of length, but it is upon you to do the experiment and use it to fill the other values. That is the time for example, 20 oscillations, the time, the period t, and maybe the value of the root of L. Remember, if we start with this particular column, the root of L, you just be finding the square root of these particular values here. For example, the square root of 0.5, you obtain it as 0.71. Then just some key points to note when you are filling the table. Always ensure that your values, for example, if this is the length column, the length for the column, the number of the decimal points should be uniform for each column. For example, this is to 0.5. It is correct to 1 decimal point. You can see that all values are correct to 1 decimal point in that particular column. Then time for 20 oscillations. Also ensure that the number of decimal points are uniform in the column for time for 20 oscillations. As you can see, this is correct to 2 decimal points. This one also correct to 2 decimal points, 2 decimal points, 2 decimal points, 2 decimal points. So if you decide to start with or to pick 2 decimal points, ensure that all values in your this particular column are 2 decimal points, or correct to 2 decimal points, because usually there needs to be a uniformity in the values in a given column. For example, period here, I've chosen my period to take 3 decimal points. So you can see that all values within the column of period are correct to 3 decimal points. So I find students making such errors. For example, you find a student recording his or her period as 1.391. Then the next value, he or she records a value of 1.56. So you see, if you record 1.56, that is correct to 2 decimal points, but this value is correct to 3 decimal points. So that is how you start losing marks. So always ensure that if you have chosen 3 decimal points, then all values within that particular column of period are correct to 3 decimal points. Same case to your value of length, 2 decimal points. If you have started with 2 decimal points, ensure that each and every value within that particular column is correct to 2 decimal points, so as to achieve the uniformity of the number of decimal points within a given column. Then of course, we know that if you want to find time for 20 oscillation, you simply displace. You are usually given the procedure to follow in the question. So you just displace the body and of course record the time for the specified number of oscillation. Like for this case, you are given 20 oscillation. Then period is usually the time taken for each oscillation. So you will just be taking the time here. For example, time for 20 oscillation, you take 27.82 divided by the number of oscillations. So 27.82 divided by 20, you will obtain 1.391. So period is usually, you simply take the time taken for a specified number of oscillation divided by the specific number of oscillation. For example, here the period will be, you will take 31.31 divided by 20. So if you divide by 20, you'll obtain 1.5 5, 6, 7. Again, you have to be very careful about the uniformity of the number of decimal points. Then here, you are asked to plot a graph of t against the root of L. Again, we know that you use your values, but you expect the graph to be a straight line graph because this is a simple pendulum experiment. So if you are given this particular graph here, of course, your graph, you just pick any two values on your graph, then you use them to plot that particular graph. Then, of course, when you are plotting a graph, you have to be careful. You include the title of that particular graph, specifying the SI units. Then you also be careful to ensure that you don't forget to label your axes, indicating T, of course, with their respective SI unit, because that usually has a mark. Then also, when you are plotting your graph, also always remember to plot all the points that you are given from the question. For example, here we are given how many points? We have 1, 2, 3, 4, 5 points. So as you can see, my graph is having 1, 2, 3, 4, 5 points plotted. So if you are given 5 points, please plot, ensure that your graph has 5 points if you want to get full marks. Then ensure that your axes are well labeled. If you are told a graph of t against the root of L, that means t will always be on the vertical axis or on the y-axis. Then the root of L will always be on the horizontal or the x-axis. Then when you are labeling the axis, always include the units specified on that particular axis. For example, from my table here, time t, that is the period t, is in seconds. So as you can see, my graph is also indicated in what? In seconds. Then against the root of L, my root of L is indicated in meters power a half. So as you can see, also my axis is having root of L, meters power a half. I find many students forgetting to include the units, and that is how you start losing your marks. Remember that in some cases, it is not necessary to include the heading of that particular graph if and only if you have indicated the units on the axis. Because if you know that you have a tendency of forgetting to indicate the units, then always ensure that you indicate the heading of that particular graph with those specific units. Because suppose you forgot to indicate seconds here and meters power half here, but you have shown them here on the heading of your graph, then in such a case, you will still be given full marks. But if you don't have the heading and you have not indicated the units on your axis, then you are always going to lose marks for labeling of the axes. Then part B, we are required to find the slope of the graph. Of course, the slope is change in y over change in x. So the change in t, that is the change in the y-axis, has the period t. So you will indicate change in t divided by the change of values on the horizontal axis, which is change in root L. Then of course you pick any two convenient points on your graph. Then of course, for example, I'm picking my point here, which is around 1.1, 2.2, and my point 0.75 and 1.5. Then of course, these particular points here, I use them, change in y. For example, here I have 2.2 minus the other y here is 1.5. So change in time axis, that is period axis, divided by change in the root of L axis, so that I have 2.2 minus 1.5, of course seconds, because this was in seconds, then divided by the change of values in the root of L, so that I have 1.1 minus 0.75. Of course, meters power a half, because this was in meters power half. So this gives me 0.7 divided by 0.3, of course, which is seconds per meter power a half. So seconds per meter power a half. So this will give me, you perform the quotient, you will get 2 seconds meter power a half. So remember, seconds meter power a half can also be represented as seconds meter power negative a half. That is courtesy of the laws of indices, which are usually learned in mathematics. Then also remember, this is an experiment, so in most cases we don't expect all the values to lie within that particular line, because in experiments we usually draw what we call a line of best fit. So lines of best fit will always pass through most of the points which are lying in a line within that particular experiment. Of course, as you can see, my values which are lying outside the line, I've also indicated them. There are students who have a tendency of rubbing these particular points that are outside the line. Immediately you do that, you are losing marks for plotting those particular points. So just leave them there, but ensure that your line passes through most of the points. Then be careful also not to leave a hanging graph. Ensure that your graph touches at least one of the axes. For example, my graph here, I've extrapolated it to touch my 0, 0. That is my time axis and also the root L axis. So avoid leaving hanging graphs. Ensure that your graph touches at least one of the axes. Then part C, I'm given that t is equals to the root of 4 pi squared L over C. Use the graph to find the value of C. Now remember, from my graph, I have t. I'm given that t is equals to the root of what? 4 pi squared L over C. But we know that all equations, that is a pendulum, will obey the equation t is equals to 2 pi root L over G. Therefore, I'll just try to play around with this particular equation such that it goes in the form of a straight line graph. And the easiest way is to ensure that I have t on my time axis, then that I have the root of L on my horizontal or the x axis. And of course, the easiest way to do that is to start by this one means that I can take square roots of each individual value. Therefore, this one means this can be rewritten as the root of 4. So I'm doing this because I already have my time here, which is on the vertical axis. Then my horizontal axis has the root of L. So I'm taking square root of each so that I obtain the root of L here. So that I have the root of 4, then the root of pi squared, then the root of L, then of course the root of C. So I'm just taking the square root of each and every value. So the root of 4, I'll get 2. The root of pi squared, I'll get pi. The root of L, I'll get root of L. Then root of C, I'll get the root of C. Therefore, I have t is equals to 2 pi root C divided by the root of C, then times the root of L. So if you observe this equation keenly, it has very close relationship with our equation of pendulum, which was t is equals to 2 pi root L over the root of G. So I've just manipulated this equation so that I obtain my root of L because I have the root of L on the horizontal axis. Then of course, from this particular equation here, you can see that the root of L is on my x axis. Therefore, I equate it to the equation y is equals mx plus c, which is the equation of a straight line graph. So as you can see, t is rhyming with t. Then x is rhyming with the root of L because here I have my root of L. Then of course, the remaining value here will rhyme with my m. And of course, we know that m is usually the slope of the graph or the gradient of the graph. Then of course, plus c. My c here is plus 0 because my graph is starting from point 0, 0. That's why my value of c is plus 0. So c is 0. Then of course, the gradient m will be equal to 2 pi over the root of c. Therefore, I'll equate my gradient m, which is 2 pi root, to 2 pi over the root of c, which is equals to my gradient. But the gradient, I had already calculated this as 2 seconds meters per power negative a half. So that means my this particular value, my gradient will be equal to, that is m is equals to 2 pi over the root of c, which is equals to 2 times seconds per meter power a half. This was seconds meter power a half. So if I want the value of c, because I'm asked to find the value of c, the easiest way is to take the squares on both sides so that I remove the square root here, so that I have 2 pi over the root of c squared being equal to 2 seconds per meter power a half squared. So I'm simply squaring both sides. So I'll have 2 squared, I'll get 4, pi squared, I'll get pi squared, the root of c squared, I'll get c being equal to 2 squared, I'll get 4, second squared, I'll get second squared, then meter power a half squared, I'll get a half times 2, which will give me meters. Then of course, I multiply both sides by c so that I have 4 pi squared being equal to that is 4c, of course, second squared per meter. Then if I divide both sides by 4, I'll get C being equal to 4 pi squared. Remember, I'm given pi as 3.14. So I simply substitute the value of pi. So 4 times 3.14 squared, then of course divided by 4. So 4 and 4 will cancel out, so that I remain with 3.14 squared, which gives me 9.8596, of course, meters per second squared. So I'm obtaining these particular values from simply cancellation of the units here. So remember, here I had remained with what? Per second squared per meter. Then of course the reciprocal of that will just be meters per second squared. So you don't have to cram the units, because you can easily derive them from your calculations. Then of course we are asked to find what does C represent. Because C is in meters per second squared, and we know those are the units for gravitational acceleration, therefore it means the value of C, that is C, represents the acceleration due to gravity, or simply gravitational acceleration. Then next we look at another example here, whereby you are told to plot a graph of t squared against x in meters. So in the experiment, you are usually given the values of the length. So assuming you are given 6.0, 8.0, 10 and 12, then you are asked to, of course, to perform the experiment. Then you are usually given a column of x to convert it into meters. Of course, we know that 100 centimeters is equals to 1 meter. What about 6 centimeters? So this will be 6 centimeters divided by 100 centimeters times 1 meter. Of course, 6.0 divided by 100, you'll obtain 0.06 meters. Again, you have to be very careful to ensure that the number of decimal points are rhyming. Remember, for the previous example, we were given the values in vertical form, but in this case you are given the values in the horizontal form. So you ensure that all the values of length in centimeters, they have uniform number of decimal points. For example, if my first value is to the nearest 1 decimal point, you can see that this one is also to the nearest 1 decimal point, 1 decimal point, 1 decimal point. Here, that is length in meters, I'm choosing to use 2 decimal points. Then you have to be very careful to ensure that all the values within this particular row are to the nearest 2 decimal points, so that I have 0.6, 0.8, 1.0, 1.2. Sometimes you can be tempted to write this one as 0.1. Remember, if you write as 0.1, that will be correct to 1 decimal point, and that will not be uniform for the values of length in meters. So you have to add a 0 to ensure that the decimal points are rhyming. Same case here, time for 10 oscillations. I've chosen my first one to be to the nearest 2 decimal points, that is 11.76. You have to ensure that the following values is 2 decimal points throughout that particular row. Same case for the period. Remember, period is you just divide by the number of oscillations. For example, these are 10 oscillations, so you just take the time here, which is 11.76, divided by 10, which will give you 1.176. Of course, I've chosen 1, 2, 3 decimal points. Then you have to ensure that all values within this particular row of period, they are to uniform number of decimal points. So because this is to 3 decimal points, this has to be to 3 decimal points, 3 decimal points, 3 decimal points all through. T squared, you just take the value of period squared. So you just square this value. That is, if you take the square of 1.176 seconds, you'll obtain around 1.38. So I've chosen 2 decimal points. So this also has to be 2 decimal points, 2 decimal points, 2 decimal points. So you have to be very careful to ensure that the number of decimal points within your graphs actually do rhyme. Then we are asked to determine the gradient of the graph. First of all, we are asked to plot the graph of t squared against x. So the points to ensure is that you have to plot all the points. For example, here I have how many points? I have 1, 2, 3, 4. So you can see I have 1. I need to have how many are these? I have I'm plotting a graph of what? T squared against x. T squared against x. So I have 1, 2, 3, 4 points. So you can see I also have 1, 2, 3, 4 points. So if there are 4 points, make sure that you plot all the points, regardless of whether, then of course you draw the line of best fit, which passes through most of the points, like for this case at least 3 points. Then you have to ensure that you label the axes with their correct SI units. For example, this was t squared. You just read here, t squared was in second squared. So you have to ensure that it is in second squared. Then it was against x. Remember, x here is representing our L, that is the length in meters. So you are told L in meters. So you have to ensure that you also indicate there your meter. So those are the points to ensure on your graph. Then you indicate when you are finding the gradient of your graph. Then for part B, we are required to determine the gradient of the graph. Of course, you just find change in t squared, that is the value in the vertical axis, divided by the change of values in the horizontal axis. And in this case, we shall have change in delta t squared, because we have t squared on the vertical axis, divided by the value of the values in the horizontal axis, which is delta x in meters. Of course, I've chosen 2 points here, so change in y I'll have 1.62, then minus the value of t squared here is 1.38, that is the vertical axis, minus the change of values in the horizontal axis. Of course, this will give me 0.24, then divided by 0.06, which gives me 4 seconds squared per meter. Again, you don't have to cram the units, you just derive them. For example, here we are dividing second squared and meter, so you'll have second squared per meter. So second squared per meter is our gradient. So for part C, we are given that t squared is equals 4 pi squared x over r plus 2 pi r over the root of n. We are required to use the graph to find the value of r. So as you can see, the value of r is in the region of the our gradient. So because this is a straight line graph, we simply compare this particular equation that we have been given with the equation of a straight line graph, which is equals to y is equals to mx plus c. Of course, you just ensure that your axes are rhyming. You ensure that t squared is on the t squared, then your x is also on the x. Remember, x axis is x, and you ensure that x is also rhyming with x. Then of course, m will be the gradient. So it means that in this case, the gradient will be equal to 4 pi squared over r. So m is equals to gradient, which is equals 4 pi squared over r, which is equals to 4, because we had already calculated our gradient as 4 centimeters squared per meter. So if I equate that, then of course, to find the value of r, I can start by multiplying each and every side by r, so that I'll have, if I pick this part here times r on this other side, I'll have 4 pi squared being equal to r times 4. Then of course, I divide by 4 on both sides, so that I get r being equal to 4 divided by 4 pi squared over centimeter, that is second squared per meter. Of course, we are given to take the value of pi as 3.142. Also be careful to strictly use the value of pi that you have been given. Don't be tempted to use, for example, 22/7 or 3.14. You strictly use the value of pi that you have been provided in the question, unless otherwise stated. Of course, if I divide that, I'll remain with pi squared. Of course, pi is 3.142. If I square that, I'll get 9.872164. Of course, then I was dividing. I'm just trying to derive the units, so that I have 1 divided by second squared per meter, which is just the same as divided by second squared per meter. Of course, when you divide, you multiply by the reciprocal, and the reciprocal of second squared per meter will be meter per second squared. Therefore, your r will be equal to 9.872164 meters per second squared, which can also be written as meters second power -2, courtesy of the laws of indices. Then part D, you are required to use the graph to determine the value of n. So remember, n here is corresponding with the value of c. So if I compare it, n is corresponding with the value of c. And remember, the value of c is usually the t squared intercept or the y-intercept. Clearly, you can see that the y-intercept here is 1.14. So that means I'll equate the value of c to 1.14. So clearly, you will take the value of c. So you will say that the y-intercept from the graph, the y-intercept, but what is on the y-axis is t squared. So t squared intercept, which is c, will be equal to, you just read the value here where the graph cuts the t squared intercept. That is what we mean by t squared or the y-intercept. So 1.14, which is the t squared intercept, will be equal to the value of c here, which is 2 pi r over the root of n. So 2 pi r over the root of n is equals to the value of c, which was of course 1.14, of course, second squared. If we want the value of n, of course, I'll start by removing the square root sign by squaring each and every side, so that I have 2 pi. No, I can start by multiplying both sides by the root of n, so that I have 2 pi r being equal to 1.14 times the root of n. Then I square both sides, so that I have 2 squared being equal to 4 pi squared, then r squared being equal to, of course, the square of 1.14, I'll have 1.14 squared. Then the square of the root of n is just n. Therefore, n will be equal to, I substitute the values of pi, which is 3.142. So if I substitute, I'll have this. Of course, you compute this on your calculator, you'll obtain n as being equal to 486 whole number 13306 over 81225, which is approximately 486 meters power negative 2. Again, you can also derive the units, because here we are talking of 4 squared. Remember, my 4 squared was in a second power 4, because 4 was in second squared, but if you square, you will get second power second squared per meter. So you simply take second squared per meter, which was my value for the gradient, second squared per meter, which is this particular 4 here. So second squared per meter. Then of course it was that particular value squared. So you also square the units, then divided by 1.14, which was in second squared. So second squared, you square it, you will get second power 4. You divide this, you will have second power 4 divided by m squared, then of course times the reciprocal, because whenever you divide, you have to multiply by the reciprocal. So on cancellation of the units, you will get meters to the power of negative 2. So we've come to the end of our class today, but we need to discuss the contribution of Galileo Galilei in the discovery of our pendulum. So this is the story that led to the discovery of the pendulum. So one Sunday morning, Galileo Galilei was attending a church service at the Cathedral Church, which was located in a city called Pisa in Italy. Then his attention was distracted by the swinging of a lamp, which was suspended from the rooftop of the church by a long chain. Now, using the beats of his pulse or his heartbeat as a clock, Galileo Galilei noticed that the time taken by the lamp to swing forth and back, that is the time taken by the lamp to swing, that is to make one complete oscillation, he realized that it remained constant even when oscillations were dying off. So in short, we are saying that Galileo Galilei led to the discovery that the period, that is the periodic time, does not depend on the mass of the material of the bulb or that particular object that is swinging, but instead the periodic time depended only on the length of the pendulum L and the acceleration due to gravity, Then Galileo Galilei was quick. He was very quick to realize the importance of the constant of time of swinging of the pendulum. And later on, Galileo Galilei imagined that a pendulum might be used to govern a clock more satisfactorily than the horizontal oscillating crossbar which were used at that particular time. And before his death, that is in the year 1642, Galileo Galilei left plans for the construction of the pendulum clock, which was first successfully constructed by a Dutch scientist by the name Christian Huygens in the year 1657. So those are the contributions of Galileo Galilei towards the discovery of the pendulum. That is, he was seated in a church and observed the lamp of the church swinging from one point to another. Then he decided to count the number of oscillations and discovered that the periodic time did not depend on the mass of the object, but it depended on the length of the object and the gravitational acceleration, which is essentially the formula for period, which was t is equals to pi root L over g. So you can see that L and g, which is the length of the pendulum and gravity, are the only variables. So what a great man he was. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button. This is Kind Tuition Academy. Let's meet in our next class.